North Atlantic volcanic activity was a major driver of climate change 56 million years ago, a study finds. And you can see the continental plate reconstruction of the North Atlantic igneous province area, subsurface intrusions, subaerial volcanism, deep marine, and various, as you'll see here, volcanic centers as well. Notice the volcanic centers very close to Newfoundland and Canada. The Paleocene-Eocene thermal maximum, PETM for short, is a period of global warming that occurred 56 million years ago, lasting approximately 200,000 years, when the Earth experienced global surface temperatures, elevations of -5 degrees centigrade. Hypotheses for this cause of this thermal short-lived warming event have included destabilization of methane hydrates, that's ice-like solids of methane and water, due to orbital forcing, changes in incoming solar radiation due to variation in the tilt of the Earth's axis in orbit, an uplift of the land causing weathering of marine rocks. However, new research in climate of the past has suggested that volcanic activity in the North Atlantic contributed significantly amounts of greenhouse gases to the atmosphere. It was active about 63 to 54 million years ago, but experienced peak volcanism 56 to 54 million years ago. Increased carbon emissions fall in line with the prominent spike of lighter carbon, C12, recorded in the shells of fossil microorganisms living in the oceans at the time foraminifera, and it enhances the greenhouse effect by trapping and absorbing heat radiating from the Earth's surface, causing a positive feedback loop of ever-increasing temperatures. This volcanism spans a vast North Atlantic igneous province, NAIP, located between Greenland, north of the UK, and west of Norway, in the total volume of magma thought to be emplaced to about 1 million cubic kilometers, equating to a carbon reservoir of 35 gigatons. To determine the contribution of the NAIP on PETM climate change, Dr. Morgan Jones of the University of Oslo and colleagues turned to the sediment record preserved on the island of Fur in Denmark, where a complete section preceding the PETM through to after the event is present, having been uplifted from the sea floor over thousands of years. And here hundreds of ash layers derived from the NAIP can be found, which the scientists analyze for particular elements to determine volcanic activity, changes in hydrology regimes and weathering. Such measurements are termed proxies and provide an indication of past environmental conditions. Then direct measurements are not, when direct measurements are not available, unlike today when we can use instruments to measure emissions in real time. Volcanic proxies include mercury and osmium that are released during eruptions and are deposited with organic matter. Their progressive enrichment through the succession indicates elevated NAIP activity leading to the PETM, therefore a fairly prompt decline during the recovery phase post-event. And this would have been comprised of basaltic eruptions and thermogenic gassing, removal of dissolved gases from liquids due to contact with magma intrusions. In the later case, high levels of methane contributed significantly to global warming, as it's a powerful greenhouse gas, 28 times more potent than carbon dioxide at trapping heat over 100-year periods. Dr. Jones suggested a distinct change in the activity of the NAIP from effusion, outpouring of lava onto the ground, to explosive, including ash clouds and volcanic bombs, for example, over this period. Paleoclimate proxies include carbon, lithium, and osmium, the latter two being tracers of silicate weathering. Lithium and osmium abundances increased during the peak and then post-PETM, highlighting enhanced silicate weathering and erosion resulting from a more intense hydrological cycle due to global warming. However, lithium measurements do not correspond fully to the paleo temperature of the time, when Dr. Jones and colleagues suggesting that uplift of NAIP would have contributed to providing more exposed rock for weathering and erosion to take place. Post-PETM weathering of the silica-rich basaltic lava flows used carbon dioxide from the atmosphere to form carbonate and bicarbonate compounds that would sequester this greenhouse gas into the rock, helping to draw down carbon dioxide and therefore aid recovery from the climatic event. In addition, an enhanced hydrological cycle transported ash to the sea for burial, which would have helped create a negative feedback loop whereby more carbon was removed from the atmosphere and hydrosphere, and thus the greenhouse forcing reduced global temperatures declined. It's worth noting that not all of the volcanic record is preserved here, as only the most explosive eruptions would have had ash reach from the North Atlantic to Denmark to be preserved and discovered by scientists millions of years later. While there's still much more work to be conducted on climate change events over geological timescales, they're important to study as they offer a window into future global warming, understanding how both natural and anthropogenic induced carbon dioxide will impact our world. And this is by Science Network, Journal Information Climate of the Past, by Morgan T. Jones and colleagues on phys.org. Please leave your comments and thank you for your support. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.